Okay. So it's my pleasure to introduce Enrica Floris from the University of Poitiers, who will talk about connected algebraic groups acting on Fano fibrations over the projective line.
Thank you very much. Thanks for inviting me to this online seminar. What I will tell you about, it comes from a joint work with Jérémy Blanc. So I'll start with a gentle introduction, just a little bit of notation. And stop me whenever something I say is unclear. So X will be always a complex projective variety. And we'll have the N1 of X. This is the set of divisors on X modulo numerical equivalence censored with R. This is a finite dimensional vector space, or maybe I would just recall that numerical equivalence means that for every curve, the intersection number of the two divisors are the same. Okay, so this is a finite dimensional vector space over R. And the dimension is called Picard number. Okay, and so this is one notion, and then I will always assume X to be terminal and Q factorial. And those are very important regularity conditions for the kind of problem I'm interested in. Well, I don't want to define terminal, just think of something which has singularities in codimension at least 3. Okay, and then still for the notation, out X will be the automorphism group of X, and out 0 is the connected component of out X containing the identity. Okay, and then the most important definition of this talk is one of Mori fiber space. So a Mori fiber space is a fibration and such that so the anti-canonical divisor of X is pi ample, and the difference of the two Picard numbers is 1. So the fibers, maybe you all already know this, but so the fibers are Fano varieties. And 2 means that the fibration is as simple as possible. Somehow. An elementary fibration in some sense. For instance, if the fibers are divisors, if B is a curve, it means that all the fibers are irreducible. Okay, so this is the Mori fiber space. Some examples. So first example, we can take a Fano variety with picard number 1 and take the product of the Fano variety with any other variety and take the projection. This is a Mori fiber space. But what I will be interested in are the other example when the fiber has picard number at least 2. So maybe this is more a remark. We consider a Mori fiber space with row of F at least 2. And F is the general fiber. Well, for instance, we can think of F as P1 cross P1, or the blow up of P2 at 3 points, which are not on the same line. And then I will set V0 as the locus of the terminal fibers. You can think of B0 just as the smooth locus of pi. Then there is an action. There is a monodromy action of the pi1 of B0 on the N1 of F. And this action is such that the N1 of F, the invariant part by this action, is one-dimensional. I will not define it, but I will try and make you a drawing. So for instance, let's say that the base is a curve. Here I am drawing a complex curve. So this is B0, this is supposed to be B0. And on top of this, we have our vibration. In the middle, there is a singular fiber, and then we take a regular one. So let's assume that this is P1 cross P1, just to have something to draw. And P1 cross P1 has 2 generators of the N1, which are the fibers of the 2 projections. And these results on monodromy tells us that if we go around the singular point, at least on the level of the N1, we can follow around the 2 generators like this. And they are exchanged. Okay. I hope the drawing is not so messy that you cannot understand what's going on. Or if, so we do the same kind of sketch. If the fiber is a blow up of P3 in 3 points, we have the 3 exceptional curves, like so. Sorry, I said P3, no, it's P2. And so when we go around, we have an action exchanging the generators of the N1. Okay. And also the existence of this action and the fact that we are assuming that the Picard number of F is at least 2 tells us that, so for instance, if B, the base is P1, then there are at least 2 singular fibers because the P1 has to be non-trivial. So non-terminal, let's say. Okay. So now we are ready to state the main result for today. Are there any questions so far? Okay, the theorem we proved with Jeremy is the following. So we consider Mori fiber space, well, Q factorial and terminal. Oops. And we assume that the general fiber has Picard number at least 2. Then we can find a closed subset proper one, so it's not the all X, which is horizontal, so its image is the OP1, and it's invariant under the action of the connected component of the automorphism group containing the identity of 0. So just be complete. Invariant means that for all G in of 0, G of Z equals Z. Z is preserved by this action. Okay, so this is the statement, and maybe before telling you something about the proof, I would like to give you some applications. And the applications are mainly to the study of the Cremona group. So what is the Cremona group? In n variables, so for me everything is over C, is the group of rational maps from Pn to Pn, which are birational. Maybe, sorry, I forgot to tell you something. Just looking at the 2 examples I made before, just to motivate the fact that the theorem is not obvious. So looking at the case of where the fiber is the blow up of P2 at 3 points, one may think that there is an obvious horizontal set, which is going to be left invariant by O0. And it is the set formed by following around these exceptional curves, right? This is a special set for the variety and has to be preserved by the automorphisms. But for instance, in the case of P1 cross P1, it's not clear at all which should be the invariant set, because P1 cross P1 is a homogeneous variety. So, okay. So this is the reason also partly why I gave you these 2 examples, because it shows that there are some cases where one really needs some results to ensure the existence of such sets. Okay. So back to the applications to Cremona groups. So the Cremona group in one variable is just PGL2, is the automorphism group of P1. And if n equals 2, sorry, this is Cremona 1. And if n equals 2, the Cremona 2 is generated by the automorphisms and the Cremona involution. This is the Noether-Castelnuovo theorem. And if n is bigger or equal than 3, the Cremona group is a very big group. Which is not very well known, although there have been recently very, very important results by, on the one hand, Blanc, Lamy, Zimmermann, and also by Lonjou and Urech. Okay, so a way of studying the Cremona group is by looking at its subgroups. And so it's algebraic subgroup. And so this is what I'm going to discuss now. So first of all, a definition. A subgroup is said to be algebraic if the evaluation map is a rational map. And so the classification of algebraic subgroups of the Cremona group is a very old problem. And if in dimension 2, in the connected case, is due to Enriquez in 1893. And for the general case, is due to Jérémy Blanc in 2008. And in dimension 3, the connected case is due to Umemura, who has a quite monumental work, a series of papers around the 1980s. And he says that, well, there are some older results by Enriquez and Fano, which Umemura quotes, but definitely his proofs are complete. And a big part of this classification has been recovered by Blanc, Panelli, and Terperot, who adopt a geometric strategy, which I'm going to explain you now. Okay, so the strategy is as follows. We have an algebraic connected subgroup. So there is a result by Weil that says that we can regularize the action. So there is the birational model of Pn, such that G is a subgroup of the automorphisms of this X twiddle, of this birational model. And then once we have this, we can run a G equivariant MMP on our birational model of Pn. So I'm not gonna give you the details of what the G equivariant MMP is, but well, many of you probably already know, but this is just a series of simple operations which take X tilde as an argument and give back as an outcome a Mori fiber space. With X birational to Pn and to our X tilde, and all these operations preserve the action of G. Okay, and also the outcome of this GMMP is not unique. And two different outcomes are connected by a G equivariant Sarkisov program. So if we have X over B and Y over T, two outcomes, they are connected by Sarkisov program, which can be found compatible with the action of G. Okay, so the study of connected algebraic subgroups of the Cremona group translates into the study of Mori fiber spaces together with an action with their automorphism groups. Okay, so this is the strategy used by Blanc-Scanelli and Terpeau. This is also this is an older, let's say, strategy which has its roots in the work by Dolgachev and Itzhaki. And so the motivation for our theorem, the theorem allows to use the geometry of the fiber and to use what we know about the geometry of the fiber to construct Sarkisov links to other Mori fiber spaces. So if we have our Mori fibration to T1 and we know something about the fiber, we can somehow we can construct Sarkisov links which are G equivariant. And I'll give you the application to the Cremona group in 4 variables that we obtain. So the theorem is the following. So we consider a Q factorial Mori fiber space. And we assume that if F is the general fiber, its Picard rank is at least 2, and F is smooth. This is a strong hypothesis. Then, so either we can find, we have our fibration here, we can find a G equivariant birational map to another Mori fiber space. And the other fibration here, this is phi, this is phi prime. The other fibration here has as general fiber either P1 or P3 or a general or a quadric in P4. So this is one case. Or F is isomorphic to one of these two Fano threefold. Either the blow up of a quadric hypersurface in P4 along the Veronese curve, and the second option is that F is isomorphic to this subvariety of the 3 copies of P2 defined by these 3 equations. So it's the intersection of 3 divisors of degree 1, 1 in 1, 1, 0, 1, 0, 1, and 0, 1, 1. And so, of course, for this result, we use the the classification of smooth Fano threefolds of Picard number at least 2 by Mori and Mukai. So we use the classification by Mori and Mukai, and a result by Codogni, Fanelli, Svaldi, and Tazin, who say which of these varieties can appear as fibers of Mori fiber spaces. Okay. And so somehow this theorem tells us that when we look at this kind of Mori fiber spaces with general fiber smooth and of Picard number at least 2 in dimension 4, the study of the associated subgroups of the Cremona 4 translates into the study of automorphism subgroups of fibrations into P1s, into P3, or into quadrics. Or there are these 2 special cases which are supposed to give interesting examples of subgroups. Any questions so far?
I have a question. So are you assuming X is has a dimension 4?
Yes. Oh, sorry. F smooth threefold. Thank you so much. Yes, yes. Here X is Here, X is of dimension 4, F is a smooth threefold. Sorry, it's an important hypothesis I forgot.
Thank you.
Thank you. Any other questions? Okay. Then I would like to tell you something about how the first result, the one on the existence of invariant sets, is proved. So maybe I'll recall you the elements of the proof of theorem 1. Theorem 1 said that for a Mori fiber space with fiber of picker rank at least 2, there is a proper closed subset in X, which is horizontal and of 0 invariant. Okay, so the first important ingredient of the proof is the theorem by Graber, Harris, and Starr, which ensures the existence of a section of pi. And my notation will be S for the image of the section. Okay, so our Z will be of the form of 0 of X dot S. So this is the set of all the possible images of points in S via elements of 0, where S is a particular section, is a section such that its intersection with minus kx is minimal. Okay. And the key lemma is a bend and break type lemma. And it is the following. So we have our pi from X to P1 as before. And we fix a section of pi and a point in S. And we're going to assume that we can find the curve in odd 0. With the following property. So every element of the curve fixes X, but the general element of this gamma doesn't preserve the old section F. Okay, and then we can find S prime and gamma, which are curves, integral effective cycles of dimension 1. Such that, so S is numerically equivalent to S prime plus gamma, and S prime is a section, and gamma is different than 0. And they are both contained in the closure of, let's say, the orbit of S under 0. Okay, is the statement more or less clear? All right, so how does the proof go, more or less? I'm going to give you just a sketch of the proof. We're going to consider nu, the normalization of gamma. And then we define the following morphism, F from P1 cross C to X cross C. It sends a point of P and a point of the pair, PG, to. So nu of G is an element of gamma, then it's an automorphism. And we apply this to phi of P and then G, where I just recall that phi was the parametrization of the section. So I'm going to show you with a drawing what F does at the level of X. This is more or less an evaluation map. So we have our X here, oopsie. Here there is P1. And have our fibers of pi. And the point X is here. And we have the section S. And then for instance, the image of F on the first variable on the X is really the section S pushed around by the curve gamma. So for instance, this is the form nu of G1 S, and then take another G2 in C, and we have nu of G2 dot S, so on. Nu of G3 dot S, etc. Right? So this is the picture on the first variable. Okay, so maybe the drawing could convince you already, but one can prove that the image of P1 cross C has dimension 2. And if we define P0 such that phi of P0 is X, we can see that the old curve P0 cross C by our hypothesis is, well, on the first variable is contracted onto X. And so we fix C bar a smooth compactification of C. And we denote by S the normalization of the closure, the Zariski closure of the image of F inside X cross C bar. And so we have an induced map, which I will call kappa, from S to C bar. And one can prove that there is a point, which I will call Z0, in the complement of C in C bar, such that the pullback of Z0 is non-reduced, is non-irreducible, sorry. And this cycle corresponds, if you look at the previous image, I want another color, maybe it's pink. Well, if we look at the closure of this image in X, we can see that there has to be something in the middle, right? And so the pullback of the zero will be this sort of pinkish cycle. This is a very, very bad choice of color, sorry. We'll switch to the green. So the pullback of Z0 will be this green cycle here, passing through the central fiber. And well, if we maybe denote by E the evaluation map, and we push forward this Z0, this is numerically, sorry, the pullback of Z0, this is numerically equivalent to S and is non-irreducible. So it will be of the form, say, C1 plus C2. It's an integral, it's a real curve. It's a cycle with positive integral coefficients. And by, for instance, by intersecting with a fiber of pi, one discovers that at least one of these, well, exactly one of these two components has to be section. And the other one has to be contained in a fiber. We can assume that C1 is a section. And C2 is contained in fibers. And this concludes the proof. Are there questions? I hope it was more or less clear. Okay, so the remark here is that in the situation of the lemma, the section S does not have a minimal intersection with the anti-canonical divisor. Why? Because so the intersection of S with minus kx is the same as the intersection, the sum of the intersection of S prime and the intersection with gamma. And so the gamma is contained in fibers of pi, where kx minus kx is ample. So this is strictly positive. So S prime has smaller intersection with minus kx. Okay, so as an application of the key lemma, I will show you the following result, which is a step towards the theorem. So the application is the following. So under, well, I will assume first of all that auth0 acts fiber-wise on X. So it doesn't permute the fibers, it acts on each fiber. This is not a very big hypothesis, but it doesn't cover every case. But so we still assume that we have our Mori fiber space, sorry, on P1 with pica rank of the fiber at least 2. So then the action of the auth0 on the general fiber cannot be transitive. So how does this go? We take S, a section, such that the intersection with minus kx is minimal. And we define the subgroup of the automorphisms, preserving the section. And then, so this actually in our hypothesis means that the section is fixed pointwise. And then we define the homogeneous variety V as the quotient of the auth0 by H. So we're gonna prove the statement by contradiction. We assume that the action is transitive, and then we have an evaluation morphism from V to F, and we send G to G of X, where X is the point where the fiber F meets the section. Okay, so by our contradiction hypothesis, phi is surjective. And we prove now that the dimension of V is, well, that phi is generically finite. The two dimensions are the same. So again, by contradiction. So otherwise, the dimension of the fiber is at least 1. And this means that we can find a curve, gamma in O0, fixing the point X, but not fixing S as a whole. And this is a contradiction by the lemma. By the bend and break lemma, as S was minimal. Well, S has minimal intersection with minus kx. So then phi is generically finite and surjective. And it is Auth0 equivariant. But here comes the other contradiction, because V is homogeneous. And so there cannot be any ramification nor exceptional locus, because they have to be in an equivariant map, they have to be left invariant by the action of the group. But V is homogeneous, so phi is étale. But F is Fano, so there are no étale maps of degree bigger than 1. So phi is an isomorphism. And so what did we do? So by our construction, we can find, we did this for a general fiber, but then we can find an open set of P1. And via this map, via this isomorphism phi, and then an isomorphism between pi minus 1 of U and U cross F. And so this is a contradiction with the fact that pi is a Mori fiber space, because we can produce via this isomorphism, if we take D1 and D2 non-numerically equivalent in F, then D1 cross 1 and D2, sorry, D1 cross U and D2 cross U, there is key closures in P1 minus 1 of U are not numerically equivalent. And so we have a contradiction with the fact that the relative Picard number has to be 1. So this concludes the proof of this application. And I'm going to stop here. Thank you for your attention.
Thank you very much. We have like 5 minutes for questions.
I'm gonna just stop sharing, but I can share again if there are some questions.
Okay. One thing.
And if you